All right, so let's look at this problem. It's a glass board, 3D internal stresses problem. So look at it online, print it out. Try to go ahead and do it on your own before I get through it, but I will kind of go through it right here. So we actually did this problem just this first half of this problem earlier in the semester when we cut it right here and we solve for fx, fy, fz. We solve for mx, my, and mz. Not really going to go over that too much, but does that make sense? I think solving for these forces is pretty easy, right? These forces at the cut counteract all these external forces. Now, solving for the moments is probably a little bit harder, but do you see that this force causes that type of moment? This force causes the same type of moment. This force right here kind of bends it over, causes a Z moment. And then this force, I think, is the only one that causes two types of moments. It causes this type of twisting, but also it causes this type, right? It causes this twisting about the y-axis, but also twisting about the x-axis. Solving and finding those internal forces and internal moments is critical, right? It's important because then we're going to take each of those and solve for the stresses. Okay. One thing that I used to do, or I like to do, is for whatever shape I've got, you can go ahead and solve for the I. For this circle, it's 1/4 pi r to the fourth. Go ahead and get a value. Also the j, we're going to use the j and the tr over j. So you can solve for the I and j for both of those. Okay, and then I like to think about, okay, each of these forces and each of these stresses could cause a, each of these forces and each of these moments could cause a stress. So I'm going to just write each of these moments, each of these forces, and kind of remind myself what type of stress does each... so there I've got the three forces and three moments. What type of stress does this Fx cause? I like to start with the axial. So here's my cut right here. I like to start with the axial Fx and the moment, the torsional moment, Mx, right? This Fx could create an N over A. This Mx could create a TR over J, whereas these other forces are the VQ over IT, right? The VQ over IT. These other moments are the bending moments, the MY over I, the MY over I. So, identify, does that make sense? That's an important step here. Does that make sense? That the X force would cause the normal stress, F over A, but the Y and Z forces would cause the shear stresses, VQ over IT. The torsional twisting X moment would cause the shear stress, TR over J, but the MY and the MZ would cause bending stresses of MY over I. All right, then let's look at this. Force in the X, it would cause a uniform. This one really doesn't matter. This one really didn't matter if I was looking at point H or point K or any other point. Let me draw this circle right here. Here's my circle, and we're looking at point H on the top, not looking at K. Excuse me. All right, sorry. Not looking at K, but we could have looked at, be able to look at any point on this cross section. For the normal force and the normal stress, it didn't matter. It is force over area. Also, be careful. This is area, not I or J. So pi by 4 diameter squared or pi r squared, either one of those. All right, so anyway, that is the force Fx. And let me think about that. Is that tension or compression? Well, it's in the negative x direction, and so the way I cut it, that's in tension. And so let me specify that in case I need to add together with any other forces. All right, now let's look at Fy. So Fy of, well, it's 0. Fy of 0, so I didn't have to look at it too much. It's 0. So now let's look at Fz of negative 100. If I've got a force at the cut of negative 100, so I've got a force right here going that way across the cut of 100, this would be my neutral axis. Then yes, there is some stress right here at H. If I was looking at this point K, it would be 0. If I was looking at this point over on that side, it would be 0. But anywhere else, it is going to have a value. And so at H, I need to do the VQ over IT. The V is just 100 pounds. All right, then the Q. The Q is going to be a tough one. Well, not too tough. You're getting used to this, right? The A prime would be half of that circle, and then the Y bar prime would be the distance to the centroid of a half circle, 4r over 3 pi. So here we've got 4r over 3 pi. That is the Y bar prime, and the area 1/2 pi r squared divided by I, which we calculated before, divided by thickness right here, 75.45 psi. What direction is it in? Well, it's in the direction that force, that negative z force was in. It's in the negative z direction. So make a note. It's a shear stress in the negative z direction in case I want to combine it with another one. Okay, now the moments. I think this torsional one is the easiest. The torsional one twists it. It twists it. This one is in the negative x direction. So let me redraw my cut right here. So here's my cut. It's in the negative x. Think about my thumb twisting, not in the positive x, but in the negative x. That would mean this top would be going over that way, that way, that way, that way. So point H does definitely have a TR over J, and it's going to be in the negative Z direction. So TR over J, the T, 3,000 pound-inches, the R, the distance, my point is away from the center of the cross-section, and then the J. Not the I, but the J. So that value, and what direction, we said because it's a negative X, in my right-hand rule, twisting about the negative X axis, this would be in the negative Z direction. All right. Now, My of 1,900 pounds. So I've got an My, a moment. Let me redraw this. I've cut it right here. Here's my cut right here. A moment about Y. A moment about Y. So Y is my neutral axis. And let's see, a positive moment about Y. A positive moment about Y would cause compression over here, tension over here, but right here at point H that I'm looking at, nothing. Right here at point H that I'm looking at, nothing, because it's on the neutral axis, because there's no bending stress at point H. There would be at K, it would be compression at K, but not at H. Okay, and let's look at this last one. Now an MZ. Let's think about an MZ, a moment in the Z direction. A moment that is twisting about the Z axis. So here, all right, I've got a moment that's twisting about the positive Z axis. Positive Z axis, my thumb is pointing that way. The tips of my fingers, first of all, here is the neutral axis. The tips of my fingers would cause this compression and this tension right here. So at point H, I do have tension of my over I. I do have tension of my over I. The m, 1,500 pound inches. The y is the distance that I am away from the neutral axis. And then the I, I've already calculated. This one was in tension, right? This one was in tension. It is pulling away from the cut. So the value right here, 45.27, and it would be in tension, which is the negative x direction. All right, so now I'm ready to look at all of these stresses. Some of them are 0 just because they're 0. Some of them are 0 because of the point we're looking at. Now be careful, this is a sigma. This would be a tau. This would be a tau. This would be a tau. This is a sigma. This is a sigma. Don't try to combine taus with sigmas. But all of the sigmas I can combine together. All right. 84, 88. Let me see right down here. 84, 88, and 45, 27. Both of those were in tension. Both of those were in tension. So there's my final answer. 46.12 psi in tension. All right, now the taus I can combine if they're in the same direction. All right, so this one is in the z direction, negative z. Both of those were in the negative z direction. Both of those were in the negative z direction. So I can say, okay, both of those are in the negative z. So here, this is how the book will do a subscript. This first subscript is the plane perpendicular to the cut. This one is the direction that it is in. I kind of prefer, I would have said tau h is 46.02 psi in the negative z direction, but that's how the book would specify. Okay? All right, that was a good one. That was a good one. And break this up into bite-sized pieces so it's a lot more manageable. But, don't memorize this one. Memorize the process. So I would say go back and look at these moments. See if you can get these moments. And then maybe these bending moments and compression, tension, or 0, make sure you can visualize how that bending moment would cause either compression or tension or nothing if it's on the neutral axis. And then, of course, VQ over IT is the tough part. Make sure you can do that Q correctly, or sometimes it's 0 because it's 0, sometimes it's 0 because of the point that we're looking at. So you've got this blank, start at blank and try to work it out on your own. And you've got this solution that you can look at. All right.